It's my pleasure to do this presentation. Our recent research fairness-aware task offloading and load balancing with delay constraints for Power Internet of Things. First, let me show you the biography of authors. Chen is currently pursuing a PhD degree in Information and Communication Engineering at Changchun University of Science and Technology. Her primary research interests include Power Internet of Things, multi-access edge computing, cooperative computing, and stochastic network optimization. Xiaojuan Chen received a PhD in Communication and Information Systems from Jilin University in 2006. She was a visiting researcher at the University of British Columbia in 2012. She is a professor at the School of Electronic Information Engineering, Changchun University of Science and Technology, Changchun, China. Her primary research interests include Power Internet of Things, multi-access edge computing, optical fiber sensing, power optical communication network. Guohua Li received a master's degree from Northeast Electric Power University. She works for Changchun Power Supply Company. Her primary research interests include power system construction, new Power Internet of Things, power marketing, and quality service. Okay, I will introduce our research in brief. We developed a two-tier cooperative edge network paradigm in PLT. We define a novel fairness indicator based on the tile index to measure the allocation balance of the system. We formulate a fairness and delay guarantee task offloading and load balancing optimization problem, which aims to minimize the allocation difference of the network while satisfying the delay constraints for multiple tasks in Power Internet of Things. We develop a linear optimization and while optimization algorithm to solve the problem. Research, both theoretical and experimental, has demonstrated that cooperation at the edge can significantly improve the performance of Power Internet of Things. Power Internet of Things connects various sensors, drives, mobile devices, machines, and Internet in power system. As the adoption of high proportions of clean energy, massive power sensors, and intelligent distribution terminals becomes more common. New applications are emerging in various aspects of the power system, and the data volume and dimensions of the sensing in the power PLT are experiencing exponential growth. A promising approach is to offload computationally intensive and latency-sensitive tasks to nearby edge nodes. Most existing studies focus on optimizing task delays, system energy consumption, and resources pricing strategy. However, only a few solutions consider the system's fairness, which is a crucial indicator of the balanced utilization of edge resources. Additionally, there is limited research on cooperative edge computing in the context of Power Internet of Things. PLT terminals are usually sensors and smart devices distributed around power facilities, which are high in quality but limited in computing capability. The sensor data in PLT often require hierarchy analysis and feedback, and which differ from conventional networks, and such as mobile networks, lines, and mass. Considering the privacy and the sensitivity of power system, power companies tend to deploy edge nodes and cloud centers independently. Therefore, investigating edge cooperative schemes that are specifically designed for PLT is necessary. Table 1 compiles the proposal presented in this paper. The following part is system model. The upper layer of the model is edge server layer, which contains edge servers deployed in substations, communication centers, and renewable energy stations. The lower layer is access point layer. APs can be computing units deployed in great roadside facilities such as TGUs, FTUs, and charging stations. APs can also be specific smart devices such as droids, robots, which should be authorized in advance in the system. The system model and the proposed two-layer cooperating edge network is shown in this slide and some equations. And this slide shows a computing model and fairness-aware model. And also the time average, the optimization problem, and P1, which aims to achieve a long-term balanced allocation of systems tasks and computing resources and multitask delay constraints. We used P1 to denote the FDD optimization problem. In P1, C1 denotes the constraints for increased stability. C2 refers to the limit on task delays, and C3 and C4 pertain to the restrictions on decision variables for achieving balance. Additionally, C5 and C6 related to the constraints on computation capacity. Importantly, the problem P1 involves stochastic programming. The decision regarding offloading and balancing are interdependent and affect the system's fairness. Additionally, given the tight coupling of variables, existing static methods experience difficulties to solve this problem. So we design an approach to solve the proposed problem based on a Lyapunov optimization and wheel optimization algorithm, as shown in this slide. Specifically, we use Lyapunov optimization to turn the FDD problem into a queen stability problem and prove this queen stability problem is NP hard in each time slot. Moreover, we use the wheel optimization algorithm with nonlinear factors to find the optimal solution and evaluate our proposed schemes. And this slide shows the partial simulation results. And this is a simulation and conclusion. This paper focused on cooperative computing and task scheduling optimization in PLT. First, we proposed a two-layer edge network paradigm for Power Internet of Things. Second, we designed a FDG to achieve a fairness-aware task offloading and load balancing scheme. This scheme considers the edge subsystems fairness, delay constraints, resources, heterogeneity, and dynamic characteristics. Third, we conduct simulation experiments to analyze the trends of indicators and systems performance. Extensive simulation results shows that optimizing collaborative computing and task scheduling among edge subsystems can significantly improve the performance of edge computing in PLT. For the simulation model presented in this paper, we focus on a limited experimental area consisting of 7 electric power communication sets and explore two um, explore two common types of PLD. In the future, it will be necessary to expand the analysis mm, and the practical PLD theories. Okay, that's all. Thank you. And this slide shows the references. Thank you.